This video will provide you with some examples of IR or infrared spectroscopy. So when we use IR spectroscopy, we use it to identify the functional group of a compound. This will be helpful when we look at other types of spectroscopy and begin to piece molecules together. So on the IR spectrum, it'll tell you what functional group is there, but it also tells you what's not there. And again, that will be helpful whenever we piece together molecules with other types of spectroscopy. The IR spectrum can be divided into two main categories. On the left portion of the spectrum, that's where we're going to look for our functional groups. And then on the right side of the spectrum, that's going to be more of the fingerprint region. Now, that region is useful because it allows us to differentiate things such as primary, secondary, and tertiary alcohols, and it also lets us look at the aromatic substitution pattern of the compound we are looking at. So on the IR spectrum, there are characteristic absorption bands or stretching frequencies. This table here shows you some of those frequencies. So this will let you identify the peaks on the IR spectrum based on the type of bond that's formed. Now, two of them to be on the lookout for, which typically stand out the most, are if we look at things such as the OH stretch for the alcohols or carboxylic acids and the carbonyl stretch. The OH stretch typically shows up around 3300 and the carbonyl stretch shows up around 1720. Those are typically the first two that I look for, and then from there derive the functional group. Now, something else of interest whenever we look at the IR are the types of carbon-hydrogen bonds. So they will show up at different places depending on their hybridization. So for instance, the sp3 carbon-hydrogen shows up less than 3000, so to the right of 3000 on the IR spectrum. sp2, they show up around 3100 to 3000, so a little bit to the left of 3000 on the IR spectrum. And then our sp carbon hydrogens will have a sharp peak around 3300. Now, again, this table is very, very, very useful. You will use it to help you identify the functional groups of compounds when we look at the IR spectrum. Now, the previous slide dealt with the functional group region of the IR spectrum. Now in the fingerprint, there are several useful things that we can get. So first off, if we're deciding between carbon-oxygen, carbon-nitrogen compounds, this is where you can look. Carbon-nitrogen bonds typically show up around 1350 to 1000. Carbon-oxygen bonds typically show up between 1300 and 1000. Now this can help determine things such as alcohol versus amine, or ester versus amide, so things like that. Now, as we mentioned earlier, we can also figure out what type of alcohol we have, the substitution on it. Is it primary, secondary, or tertiary? Primaries typically have a peak around 1050, secondary around 1100, tertiary around 1150. Another useful thing from our IR is we can determine the aromatic substitution pattern. Okay, so in combination with other types of spectroscopy, NMR specifically, we can figure out where the groups belong on an aromatic ring. Now, whenever we look at this table, these boxes, so for instance, well, first here, these are our wave numbers on the spectrum. Now the boxes represent a peak. So if we look at the mono-substituted benzene, we see that there should be two peaks on the spectrum. So for instance, there should be a peak around, if we follow it down, around somewhere in the 750 area and around 700 for the mono-substituted. You can use this chart to look at the peaks in the fingerprint region to figure out the aromatic substitution pattern. So now let's look at a few spectra. And the question that is typically asked with IR is, what is the functional group? So for our first one here, what sticks out? Well, we have this stretch here around 3300, so that is going to be our OH stretch. Now, that's one of the first stretches to look for. I previously mentioned that it's also helpful to look for carbonyl stretches around 1720. If we go around 1700 or so, which is around here, we do not see any peaks, so we do not have a carbonyl. Now also we have a good peak around 1250, and that's going to be our CO stretch. So since we do not have a carbonyl, we have an OH stretch and a carbon-oxygen stretch. This means that this compound should be an alcohol. So that's our functional group for this spectrum. Again, the OH stretch is usually pretty evident. It's the broad stretch around 3300. So this is kind of a characteristic of our alcohols and what they will look like. However, the OH stretch does not always have to be super broad, as like it was in the previous example. So, for instance, in this spectra, this is also an alcohol. In this spectra, we do not see the broad OH stretch. However, it is still there, okay, because we still have the OH stretch, and then we also have our carbon-oxygen stretch. But what accounts for the difference really is how the sample is prepared. So let's look at some more spectra. So on this spectrum, what stands out? Again, I would recommend looking first for OH stretches and carbonyls. All right, so this huge peak here around 1720, this is our carbonyl peak, okay? So we do have a carbonyl, so our functional group is going to be one of our carbonyl-containing functional groups. Now, you also may notice this very broad stretch over here. This is the OH stretch, okay? So with a carbonyl, an OH stretch is more spread out kind of, and it's sharp, it's not as broad. Now, so what's our functional group? Well, if we have a carbonyl and an OH, that means the general structure would look like this, and that, the functional group name for this, is a carboxylic acid. So this spectra is one for a carboxylic acid. What about this one? Well, let's start out by looking for OH stretches and carbonyls. We do have a very sharp peak here again, which is around our 1720 mark. So that's a suggestion that we have a carbonyl containing functional group. Now, over here to the left, where we would be looking for an OH stretch, we do not have one. So that means that we do not have a carboxylic acid or an amide because there's no NH stretch. Now, This is one that's a little more complicated. Since we don't have any other good indicators on this spectra, this is going to be the characteristics of a ketone. Especially since there's no Fermi doublet. If we were thinking aldehyde, there would be a Fermi doublet over here. However, since there is no Fermi doublet, this is a ketone. All right, let's look at another one. What stands out on this spectrum? Well, on this spectrum, we have a huge peak again around the 1720 mark, so we have a carbonyl. Now, we also note that this carbon-nitrogen stretch shows up typically around 1230 to about 1020. So somewhere over here we have as a carbon-nitrogen stretch. And then we do have nitrogen-hydrogen stretch over here that's very kind of like faint, but it is there. And then one more thing that's kind of different about this spectrum is if we look at the carbonyl peak, there are around 2 different little peaks at the carbonyl. That is a characteristic of an amide. Also, since we have a carbon-nitrogen bond, that's also going to be an amide. Again, so the general structure for the amide would be the carbonyl attached to the nitrogen. Now, notice that you can't really predict the overall structure of the compound. That requires NMR spectroscopy. But we do know the functional group is an amide. All right, what about this spectra? What sticks out? Well, again, typically, look for the carbonyl. We have this huge peak at 1720 or around 1720, so that's suggesting carbonyl. Now, then we can look for OH stretches or NH stretches over to the left, or around 3000 before it. There's no apparent OH or NH stretch. What other peaks do we have? Well, around 1300 here, we have a CO stretch. So if we start thinking about our carbonyl chemistry, which functional group has the carbonyl bonded to an oxygen? So the general structure would look like this. And that is what we call an ester. So this is the spectrum for an ester. Now, for aromatic compounds, when we're looking at the IR spectrum, there are typically 4 things to look for. So first, we want to look for an sp2ch stretch, which will be to the left of 3000. We want to look for overtones, which are going to be weak peaks at the top of the spectrum around 2000 to 1600. You want to look for the carbon-carbon double bond stretch. And then we want to look for out-of-plane bends, also abbreviated as OOP bends, in the fingerprint region. Now, this will also help us determine the substitution pattern of the aromatic ring with that table we looked at earlier. So if we look at a spectrum of an aromatic compound, for instance, metaxylene, this is what we're looking at. So notice that we have our sp2ch stretch to the left of 3000, overtones, which are these peaks here. These are the overtones. We also have our carbon-carbon double bond stretch, and then we have our OOP bends in the fingerprint region. So whenever we're looking at the fingerprint region to determine the substitution, it's typically going to be to the right of 1000. We're going to be looking at these peaks over here. Okay, and I identified them as around 900, 800, and 700. But how would we know that this is meta-substituted? Well, if we look at the table that we were looking at earlier, let's see what we have. So if we have the peak around 900, 800, and 700, okay, so that means that we have 3 peaks. Okay, and those were around the frequencies they showed up. Then we can look at our table. So we're looking for one of the substitution patterns that produces 3 peaks. So for instance, the mono-substituted only has 2 peaks, so we can cross that out. Ortho only has 1 peak and cross it out. Meta has 3 peaks, so we can keep that one. Para only has 1 peak. 124 only has 2 peaks. 123 only has 2 peaks. And then 135 only has 2 peaks as well. So that automatically shows us that this one is meta-substituted. And again, let's look at the sizes to make sure that they all match up. So we would expect 1 peak around 900, 1 peak around 750 to 800, and another peak around 700. So since this is what our spectra look like, we can say this one is meta-substituted. Now for IR spectroscopy, the more spectra you see, the better you will be.